models. Now, we say that over root, you can use, in principle, you cannot use purely empirical statistical models for over the rooftop model, because you need somehow some information on the profile of the leak. So those are so-called hybrid models. Because they use some information on the local environment. In particular, they need the link profile of the link, from the transmitter to the user that is on the ground. And to do this, they all use a knife edge approximation of the link profile. Let me show you what I mean with this, with a slide. Okay. Now that's how the over rooftop models work. We start from the real scenario where you have the base station on top and the mobile users on the ground. And as I said, we assume that the propagation is along. It's actually what happens. The dominant component is coming from above the roofs. So you take the real scenario. The first thing that you do, you build an equivalent scenario where you replace the buildings with solid blocks that roughly represent the building. You cannot include all the details, all the fine details of the building, because it is impossible. So you just reproduce the main features of the building. So you build an equivalent scenario. And then you convert the equivalent scenario in the so-called theoretical scenario, where you have a series of knife edges, each one representing the perimeter. So usually those knife edges are located in correspondence of the most important points where things happen. You can even model an entire building with a single knife edge. So what the over-the-rooftop model does is you compute all the losses, extra losses, due to those knife edges up to here, and then you compute the last piece of radio link using a deterministic method. So in this sense, this model is hybrid, because you need anyway a description of the scenario. So let me. A lot of work has been done in the past to develop those over-the-top models. Let me just present you briefly the way what we call the Italian national GSM model is. And let me tell you why we do need a national model, first of all. The problem is mainly the reason to have a national model for the prediction of the coverage is mainly legal, because when the mobile the GSM system was deployed, companies that were licensed to do that were required to guarantee a given coverage of the national area, of the national territory, 80% and 90, 95, etc. How do you calculate that coverage? The coverage depends on the model that you use, because if you use two different models, provided that you cannot measure every single point of your territory, so you have to use models. If you use different models, you get different results. So from a legal point of view, it was important to have a single agreed model that could be used to evaluate the coverage. So we ended up with the Italian national GSM model. I think other countries have done the same. But I know this and I present you this. But the idea is the same. We're talking 90s, during mid-90s, when the GSM thing was catching up. Now, again, what this model is predicting are losses. And the model is simple. It says, we're talking about over-rooftop propagation. We use losses, what we call base losses. That is the losses that you calculate with the Okumurata model. So you take the Okumurata model and you calculate the losses. On top of those losses, you have the losses due to knife edge diffraction, because you are propagating over the rooftop. And those things are calculated with the, you already know it, the Epstein-Peterson method. Don't worry, we will do exercises on this method. I know you are happy, you are looking forward to that. Peterson. And since we were not happy, we introduced another environmental correction factor that was taking into account the environment. Now, I give you the numbers because it is, I think it's a good way to set up the model. The F parameter is a correction factor that you apply, and depending on the environment, And to classify the environment, we just take into account the percentage of built-up area. So you take the percentage of built area, so if it is greater than 35%, we say this is a high density urban. And we introduce, look, the sign here is negative, so this will be an extra losses of 6 dB. Then if the percentage is between 15% to 35%, this is medium density, and we actually reduce the losses by a small amount. If the percentage of built area is between 8 and 15, this is low density, and we reduce the losses by 10 dB. Then 3% to 8%, we call that suburban. Obviously, those coefficients have been tuned to the way we build cities. So this is something you have to, if you want to use them, maybe you can use them as they are, or maybe you have to adjust them to your proper situation. But the basic idea does not change. Now, everything that is lower than 3% is classified as open area. And we use open area with vegetation. Vegetation, we mean trees. 24 dB. Open area, no vegetation. 29 dB. And if you are running over water, because you have lakes or whatever, obviously there is no built area of water, 32 dB. So this is what was agreed among between the government and the phone companies, and this is the model that has been used to assess the coverage from a legal point of view. Obviously, you can do whatever you want, but then you have to, if you have to bring things in court, you have to use something that is legally defendable. Otherwise, it's no value. So, if you want to build your whole model, you have all the bits and pieces. You have the model, you have your Kumura-Hata models, you know the Epstein-Peterson model, you can use those coefficients. If you're really motivated, I'm not sure. Okay, questions before we move to the next topic. It is always related to this. We will do some exercises later on where we calculate this. We don't take into account the environmental factor, but we will just calculate those two quantities. Yes, RDP, yes, the people in there. But since there is a minus sign here, those values actually reduce the loss. So the losses, for example, where you have no vegetation, will be 30 dB smaller, so the signal will be 30 dB stronger than what will be without the. That's a correction factor due to the fact that the Okumura-Hata model and the Epstein-Peterson, but the Okumura-Hata has been studied and developed for urban areas. So when you go to open areas, you have to correct the model's prediction.
You want to do that.
Okay? No other questions?
This model is practical in theory in Ecuador.
Sorry?
This model is practical in Ecuador.
Practical?
In
Ecuador? I would think so, yes, I would think so. Because your urban structure is not very different from the structure, from the Italian urban structure. You don't have skyscrapers, very few. Your buildings are 3, 4, 5 stories. Concrete, reinforced concrete, so it's very close to what we have. The American environment, North American environment is very different because you have a central city with very tall buildings, with skyscrapers, and then you have a suburban area with villas, so with very small, and this is not the case in Europe. Europe is completely different. So this model works for Italy. I think it will work reasonably well also for your environment, for your cities. It's very simple. Other questions? A little bit more of theory that is reached to exercise. As promised. Okay. What I anticipated this morning is that the coverage prediction process is a two-step process. First, we predict the median field strength. And this is what all the models that we have seen so far do. So, Okumurata, Atalike, Exi, whatever, they predict the median field value. Then you have to predict fluctuations. Around the nearby.
Foolish.
And we have not yet done that. Your prediction procedure must make this next step, otherwise your predictions are worthless. Now, the median field strength is also called dominant component. And then we have the fluctuations. Fluctuation is called the fluctuations are also called the fading components. Those variable, those fluctuating components can be decomposed into two contributions. The so-called slow fading and fast fading. The fast fading is also called, for a reason that I will explain in a moment, shadowing. Shadowing. And it's due to the fact let me see if I can show you something before we enter into this. Let me see. Okay. Let me Okay, let's start to understand those components. Let's start from what you find when you measure
como desapareció,
signal
no fading, como
received
que
by a
lento,
mobile
como
unit.
desapareció algo así.
Okay, this is as a function of distance of this mobile unit, the signal that you receive in a log scale, so can be dBm. This is quite a short tree. It's not an incredibly long tree. But you can see that the continuous line is the signal that you actually receive. And the dashed line is a kind of moving average. So you are smoothing, is a smoothed average of the signal that you receive. Now, if you were on flat Earth, you would receive something like that. If you actually work out a prediction taking into account the environment, your models predict something like that. This is actually quite a good agreement with the prediction. This would be the median, the red line is the median co-predicted component. And on average it's okay. But you can see that the actual signal has two fluctuations. One that is the one by the dashed line is very slow. Slow means slow in space. If the mobile moves, then it is slow in time. That's why we call it slow fading. Because since we are usually talking about mobile units, it is slow in time. But it is really quite slow in space. What is the reason for those fluctuations? For those slow fluctuations of the signal? What do you think would be the reason? Those slow fluctuations are due to changes in the environment when you move. For example, obstacles coming or exiting from your scenario. If you think about, imagine that you are moving along the road and you have a transmitter here, then you will have visibility up to here, and you will have shadowing by this building, and then maybe visibility again. So when these kind of obstacles that are quite large, buildings, etc., enter or exit your scenario because you are moving, they are fixed, but you are moving, they cause this very slow fluctuation. So here you have more signal, here you have a little bit less. On average, what you get is the red line. This is one, so the reason for slow fading component, for the existence of slow fading component, is changes in the environment. For example, obstacles entering or exiting the scenario. This is quite possible because since we are talking of values that have been calculated on areas that are 500 meters times 500 meters, it's quite possible that when you move within this pixel, the objects, the obstructions changes. Okay, so we are talking of fluctuation on area that are 500 times 500 meters squared. So it's quite possible. And then you have those fast fluctuations. What are those? What is the reason for those fast fluctuations around the slow variation? What do you think would be the reason for that very fast fluctuation? We will see this in details later on, but think about it, we are in a urban environment. There are a lot of reflecting surfaces. There are buildings that are reflectors. They are everywhere. So we can expect a lot of reflected electromagnetic rays reaching the receiver. And what happens when you move a little bit from one point to another? Think about antenna diversity. What happens when we move when we change the antenna to an antenna that is a little bit further? All because you go from a positive to a destructive combination. This is exactly what happens when you move around. You go from a point where there is a destructive combination to a point where there is a constructive combination. And we will see that this distance, since we have a lot of electromagnetic rays, not only two, but a lot of them, this distance is very short. It is the order of the wavelength. I'm sure you have experienced, you know that this exists. And you have experienced this a lot of time in your life. When? All of you. You are not, maybe you're not making the connection now, but this is exactly what we're talking about. You are in your car, you are listening to the radio, you stop at the traffic light and you don't hear the radio anymore. You move 10 centimeters and the radio is back. That's because you just parked in one of those very deep notches. The scenario does not change if you move the car by 50 centimeters. Cannot change. So the deep zero signal that you find is due to the destructive interference of the electromagnetic rays. You are unlucky and you park your car, you stop your car here. Then you move it a little bit, boom, and the signal jumps up. This is fast fading. Fast fading is due to the combination of multiple reflected but we will discuss this next time. Now we switch to exercises. Question before we do that? Okay. One more exercise on the Fresnel ellipsoid. This is a slightly different one. Okay. We want to install a satellite station at a frequency of 10 gigahertz.
Wow.
With an elevation. Sorry, this exercise is tailored for our latitude, 37 degrees. You would have possibly, I think, for something much closer to 80 degrees. So, but does not change. So the satellite is a geostationary satellite. And you have to determine what is, calculate, the maximum allowable satellite of an obstacle you can model it as a knife edge, a very thin obstacle located at a distance of 50 meters. In other words, I have an obstacle here. You can imagine it is reasonably thin, so you don't have to worry about it. At a distance of 50 meters. I want to know how tall can be this obstacle. Someone wants to build something and I have to tell him, okay, you can go up to 10 meters, 20 meters, 50 meters, 100 meters. You are looking at a geostationary satellite. You may not need the distance of the satellite. Just you know that the distance of the satellite is much, much further away than the object close to the Earth. If you need a distance, it's 38,000 kilometers, but it's a lot. You will be able to do some simplifications. So it's interesting to see how you tackle this problem. H. Okay. Now, as usual, the idea is that we have to keep the first Fresnel ellipsoid free from obstacles. Now, to do this calculation, we simplify our geometry a little bit. But now we have a distance R1 to the obstacle and the distance R2 from the obstacle to the satellite. And the distance R2 is much, much larger, obviously, than R1. So, if we call this rho, this is not, obviously, the semi-axis, because we are not in the center of the Fresnel ellipsoid. We are just drawing it at the very beginning of the Fresnel ellipsoid. If you look to your page through your notes, you will find that the equation. Sorry, wrong. I used wrong. Sorry. The equation that defines the Fresnel ellipsoid is that one. And this can be solved for the unknown rho, that is the sides at the distance in that particular point. Now, since we are on the planet Earth, it is reasonable that the distance from the ground to the satellite is much, much bigger than the distance from the Earth station to the obstacle. If this is the case, then you can neglect, sorry. As far as the denominator is concerned, you can neglect this, because this is going to be much, much smaller than this. And then you can simplify this with this and obtain an approximate equation for the dimension that obviously is valid only as long as you are very close to the ground station, but really you don't need R2. So now we calculate the wavelength, which is 0.03 meters for the frequency of 10 gigahertz. And all we need now is R1. And as a first order approximation, if you ignore those angles just like that, we are just applying the method. R1 is the distance d divided by the cosinus of this angle. So it's about 63 meters. Now the sides rho around that point of our Fresnel ellipsoid will be 1.4 meters. Now if you really want to know, if you want to be safe, you can back project this segment to here and obtain this delta H as rho, again divided by cosinus of 37 degrees. And this will be slightly bigger than 1.5, 1.75 meters. it's a good approximation. We don't have to be too picky. So the maximum allowable height for your obstacle will be this length that again can be computed if you know the distance and the angle. So the total height will be the distance times the tangent of 37 degrees. That is 37.6 meters. This is the total height from this point to here. But your building can be only high. Maximum allowable height would be around 35.8 meters. In practice, you want to leave an extra space, extra safe margin, because you want to keep free also the second and third Fresnel. But this gives you an idea of what is the region in space that you have to keep free from obstacles in a satellite.